Hi, I'm Zor. Welcome to Unizor Education. Today we will start a new chapter called Hamiltonian. So today is Hamiltonian Introduction, kind of short, just to basically introduce you to the main concept of Hamiltonian mechanics. And this is more, I would say, mathematical rather than physical. However, it's very important to actually understand that it leads to some more physical approach to equations of motion. What do we know as of now from the previous chapters, Lagrangian and Noether Theorem? We have related the equations of motion with Lagrangian. Now, equations of motion is basically Euler-Lagrange equations, and let me just write it down. It's partial derivative of Lagrangian by coordinate is equal to time derivative of partial derivative of Lagrangian by generalized velocity. So this is the main Euler-Lagrange equation, which we basically derived many times, explained, etc. Now, what is Lagrangian? Well, in simple, relatively, in classical simple cases, Lagrangian is difference between kinetic and potential energy. Now, this difference, which is called, well, it's Lagrangian, but I mean, what's the physical meaning of this? Well, to tell you the truth, I feel very uncomfortable with interpreting t minus u from the physical standpoint. I don't know basically what physical sense is in this difference. So it feels uncomfortable. What else is uncomfortable? Well, this is the second order differential equation. You see one derivative, another derivative. So it's the second order. It's always difficult to deal with, much easier to deal with the first order, with the first order differential equations. So there are certain draw points in this approach. Now, Hamiltonian mechanics kind of eases this out a little bit. So we will convert basically this model into another model, which is Hamiltonian mechanics, which looks simpler. And going forward, I can tell you that Hamiltonian mechanics and all these whatever formulas are related are much more suitable for contemporary theoretical physics like quantum mechanics, statistical mechanics, and others. So this is basically the motivation for us. Now, this chapter of this particular course is dedicated to basically research what is the Hamiltonian mechanics and how it really looks like from mathematical standpoint with equations, etc. And this is all part of the course called Physics Plus. It's presented on unizor.com, totally free website, no subscription, no advertisement, no signing in, just pure knowledge for your consumption. So let me basically start with this thing and try to do it maybe a little bit better. Okay, so first of all, let's just concentrate on one very simple thing. In the previous lectures, primarily in a description of the Noether theorem, we were talking about generalized momentum, which we defined as partial derivative of Lagrangian, which is basically a function of time, generalized coordinates, and generalized velocities by generalized velocity. So we have defined it as momentum, generalized momentum. It's a definition, basically. Now, obviously, when I'm writing just Q, I mean Q1, Q2, Q3, etc. It's generalized coordinates. Okay. Now, why is this making sense? Well, look at the Euler-Lagrange equation. What can we do right now is to rewrite it as dl by dq is equal to time derivative of this, of the momentum. So time derivative is, in Newtonian notation, is just a dot. So dot is time derivative here and here. So this looks much better than this, right? Well, what's the problem? The problem is that we have only n equations of the second order. Here we have also n equations of the second order, but here we have n different unknown variables, which are functions q of time t. Here we have 2n functions, q as a function and p as a function. If we want to consider this as this simple thing, we should consider them to be independent. So this is basically a very important moment. We are considering momentum, generalized momentum, and generalized coordinates independently. So this is something which you really have to kind of understand, because in classical mechanics we know that momentum is mass times velocity, and velocity is time derivative of coordinates. So they are related. Here we are considering them independently because it's not the old-fashioned classical mechanics. So if we are considering them independently, because otherwise we cannot really bring it to a first-order equation, then we have a problem of not having sufficient number of equations. We have 2n independent variables, but only n equations for each I, basically, right? So it's for each I, for each coordinate. So that's a problem. And now I'm introducing a very easy solution to this problem, which leads us to Hamiltonian equations. And here it is. Let's just recall that in most of the classical mechanical simple models, simple mechanical systems, we have this thing where t is a function of what? Of velocities, and u is a function of coordinates. Kinetic energy does not depend on position. It's basically, you remember, mv squared, and v is actually, q is a dot, time derivative of coordinate. And potential energy depends only on position, which means on coordinates. So, in classical mechanics, we know that q and p are related. So I would like actually to have it rewritten as function of p somehow. So what is this? Well, the kinetic energy is mvi squared for all different, it's kinetic energy of the whole system. So vi is the velocity of each particular component of that system. Now, if instead of this I will put this, that's the same thing, right? P is mv, square would be m squared v squared, divided by m, it would be this. I really have to put 1/2 here, I'm sorry. So that's the definition of T, kinetic energy. Okay, fine. So now, if I'm using this particular definition for this, I can come up with the following thing. So if t is equal to 1/2 sigma 1 over mi pi square, then dt by dp I would equal to, so for one particular I, so it's a square and 1/2, so it would be 1 over mi pi, right? Okay, and what is this? Back to p is equal to mv. So if I divide it by m, it would be v, right? So it's q with a dot. Now, this is an interesting equation. Now, this is also an interesting equation. So let's rewrite this as t minus u. Now, we know that kinetic energy is independent of coordinate. So this is actually minus du by dqi. T is independent on q1. Q depends on qi. It depends on the velocity. So we have an interesting two equations. One is this one. pi is equal to minus du by dqi. And another is this one. pi with a dot. qi with a dot is equal to dt by dpi. Look at the symmetry of this. It's definitely much better. And now we have two n equations. What's the problem? Well, the problem is that the first one is a function of potential energy, and the second one is the function of kinetic energy. And these are two different functions, and this is really doesn't look good. However, we can definitely very easily repair it. Again, t is independent of q. It's a function only of momentum. Now u is independent of momentum and it's function of coordinates. So what I can do is I can put here instead of u, I can put t plus u. And it doesn't really change anything because t is independent of coordinate. Instead of this, I can put also t plus u because u is independent of momentum. It depends only on position. Now I have the same function, right? I call this function Hamiltonian. And now my 2n equations now look like this. Now we have two n independent equations where qi and pi are independent variables, n variables each, and n variables this. We have two n different differential equations of the first order, and quite frankly it looks much more beautiful than this one. So this is the main kind of road which introduced us to Hamiltonian mechanics. And what's one of the very important issues for myself, what is this? well, this is the sum of potential and kinetic energy, which is total energy of the system. So in these relatively simple mechanical systems, whenever this thing actually is an energy, we have some meaningful system of coordinates, a system of equations, where the function from which we do this partial differentiation is energy. I mean, it has certain meaning much more than this one, the difference between kinetic and potential. So this is the main road where we introduced a concept of Hamiltonian. In classical simple cases, it's full energy of the system, mechanical system. Again, everything basically is related to conservative mechanical systems. We have certain forces like gravitation and something like this, the forces which have the field, and it's conservative forces. So in all these cases, like planets are moving around the sun along their orbits. I mean, this is typical example of conservative system. So, and in these cases, we have this particular thing. So obviously it's very natural to generalize it to generalized coordinates, and in as much as we need the Lagrangian as a function which characterize the behavior of the system, we need, for this theory, for Hamiltonian mechanics, we need Hamiltonian to basically describe the system. And then the system of equations would be much more beautiful, if you wish. I mean, I do like how it looks much better than this one, although there are two n equations and only n here, but each equation seems to be much simpler. So the more complicated problem we have divided into more less complicated problems. And then each particular problem is easier to resolve because it's a first order rather than a second order equation. So as a result, I can say that the Hamiltonian mechanics is used in many different contemporary theoretical physics fields. For example, statistical mechanics, quantum mechanics, and some others, which I don't even know myself about. Okay, anyway, so that's it for today. I do suggest you to read notes for this lecture. Every lecture on Unizor.com has video part and a textual part. Textual part is similar to a textbook. So I suggest you to read. That would be, you go to Unizor.com, you choose Physics Plus course. The chapter is called Hamiltonian, and then that's the first lecture called Introduction to Hamiltonian. That's where you will read whatever I was just talking about. So thank you very much, and good luck.